Welcome back to Probability and Statistics 1. These are supplemental slides to Unit 2 on counting. How we're going to use mathematical techniques to count how many elements are in certain finite sets. So the first principle is pretty simple. If you have two sets that have no overlap, so they're disjoint and they're finite, then the cardinality of the union is simply the sum of the two cardinalities. That's pretty easy to see, and of course it hinges on the fact that there's no overlap between the two sets. So that's why you're not, over counting anything when you just add cardinality of A and cardinality of B. The inclusion-exclusion principle applies to counting elements of sets. We've already seen the principle as it applies to probability. And it's very similar when it applies to just counting. So if you've got any, finite sets whatsoever, if you look at the union of any of two of them, A union B, then the cardinality of that would be the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. And the reason why is that, that minus the cardinality of the intersection compensates for the overcounting in cardinality of A plus cardinality of B, because in that, when you just add cardinality of A and cardinality of B together, you've counted elements in the intersection twice. And so you need to subtract off the cardinality of the intersection to restore, right, every element being counted just once. The pattern continues for a union of any finite number of sets. So if you have three sets, the cardinality of the union of those three would be the sum of the individual cardinalities, right, minus the cardinalities of all pairwise intersections, and then plus the cardinality of the intersection of all three. And a similar kind of logic here applies. When you add the individual cardinalities, you've counted things in the intersection of any two of the sets twice, and so that's why you have to subtract off the pairwise intersections. But when you do that, you think about an element that's in the intersection of all three sets. It was counted three times in cardinality of A plus cardinality of B plus cardinality of C, and then it was subtracted three times in that subtraction of the pairwise intersections. So you have to add back the cardinality of the intersection of all three sets. And this pattern continues for any finite union of sets. The formulas get a little bit, cumbersome, but it's easy in principle to sort of see what happens. So here's an example. There are three clubs. Each club has 24 members. Each pair of clubs has 8 members in common. And then there are 2 individuals who are in all 3 clubs. So the question is, what is the combined membership of all 3 clubs? How many individuals are in all 3 clubs? So let's use some notation here. Let's let A be the set of members of the first club, B represents the members of the second club, and C represents the members of the third club. What we're after here is the cardinality of the union, right? The union of those 3 sets. By inclusion-exclusion, that's given by our formula there, the sum of the cardinalities minus the cardinalities of all pairwise intersections, and then plus the cardinality of the three-way intersection. So we know all those numbers. The individual clubs have cardinality of 24, so we get 3 24s added in. There are 8 members in common for every pair of clubs, and so we get those 3 8s subtracted off, and then finally there were 2 members who are in all 3 clubs, so that's plus 2, and that turns out to be 50. So there's 50 individuals in all in these clubs. You can actually go further than this. Once you have that information, you can actually break it down completely and sort of get a complete picture of what's going on. Let me go back. There's our 3 clubs, right? And we now know there's 50 members in all. Now, we also know that there were 2 members in the intersection of all 3, so there they are. We were given that there are 8 members in the intersections of any pair, two of those members we already see, so the other 6 must be in the little leaves there, right? So that gives us now what we said before. We now have 8 members in every pair of clubs. And then finally, each club itself had 24 members. So if you look at, for instance, A, we've already got 14 there. So there must be 10 in A that we haven't counted so far. They must be outside there. And the same would go for B and C. So now you can see exactly what's going on in each of these clubs. There are 10 individuals who are in exactly one club. And then in each club, there are 6 individuals who are in exactly 2 clubs. And then in each club, there are 2 individuals who are in all 3, right? So that's the inclusion-exclusion principle. Here's another principle of combinatorics, how to count. It's called the multiplication principle. If you've got a 2-stage process, and in stage 1 there are m possible outcomes, and then independent of whatever outcome occurred in stage 1, stage 2 is going to have n possible outcomes, then there's going to be m times n possible outcomes of stages 1 and 2 combined. And that's kind of easy to see if you think about sort of this like a branching tree sort of diagram like I have here. You can see the first stage of the tree has 2 possible outcomes. They're the dots in blue there. But no matter which of those outcomes you look at, the next stage has 3 possible outcomes. And so that gives us 6 possible outcomes in total. And so it's a pretty simple principle, but it's remarkably powerful. It applies in a lot of situations. So let's take a look at some examples here. How many distinct permutations of the letters in the word slogan are there? Well, a permutation is just a rearrangement. So you can think about that as a multi-stage process and use the multiplication principle. There are 6 ways to pick the first letter, and then no matter which letter you pick first, you got to pick a different letter for the second letter, so that'll be 5 ways for that. So there'd be, right, 6 times 5 are 30 ways to pick the first 2 letters. And then you've got the third letter to pick. Well, now there's 4 remaining, so there's 4 ways to pick the third letter. So you get 6 times 5 times 4, and so on. So ultimately, to rearrange all 6 letters, it would be 6 factorial, or 720 distinct arrangements or orderings. This is called a permutation of 6 things taken 6 at a time, and the number of permutations of, in general, n things taken n at a time is going to be n factorial. And we use this symbol npn to denote that. Here's another example. Now pick any 3 distinct letters from slogan and arrange them. How many possible outcomes are there now? Well, this is sort of just an abbreviated version of the first problem, right? You've got 6 choices for the first letter, 5 for the second, 4 for the third, so the answer would be 6 times 5 times 4, or 120. This is called a permutation of 6 things taken 3 at a time. And in general, that number, the permutations of n things taken r at a time, where r is less than n, of course, or less than or equal to n, would just be n times n minus 1 times n minus 2, and you keep counting down until you have r factors in all. So the last factor is going to be n minus r plus 1. And it's pretty easy to see that that number is just n factorial divided by n minus r factorial. If you look at that, you get just the kind of cancellation you need to get that product of r factors that we need. So that is the number of permutations of n things taken r at a time. Another example, let's now pick 3 distinct letters from slogan, but we don't care about the order. We just want to know how many possible ways are there to pick 3 letters. We don't care about the order in which they're picked. So essentially, we're just picking a subset of size 3, right, from the set of letters, the set of 6 letters in the word slogan. So let's call the answer 6 choose 3, and I use that symbol 6C3 to shorthand for that. This is called a combination of 6 things taken 3 at a time. So the difference between a combination and a permutation is that a combination doesn't regard the order. Order doesn't matter in a combination. Order does matter in a permutation. Now we can answer the question by thinking about it in kind of a clever way. Uh, if you think about the number of ways to order three objects from a set of size 6, right? Think of that as a two-step process. To order three objects out of a set of size 6, first you would pick the three objects you want, and there's 6 choose 3 ways of doing that, just sort of by definition. Still don't quite know what that number is, but whatever it is, there's 6 choose 3 ways to pick 3 elements from a set of size 6. And then, from what we've done before, to order those, there's going to be, order those 3 elements we picked, there's 3 factorial ways. So that's a two-step process that ultimately results in a permutation of 6 things taken 3 at a time. So the number of permutations of 6 things taken 3 at a time has to be the number of combinations of 6 things taken 3 at a time the number of ways of ordering those 3 things. That's 3 factorial. So you can solve that for 6 choose 3, and you get 6 choose 3 is 6p3 divided by 3 factorial, or 20. In general, that same logic leads us to the formula we have here. N choose r is n factorial divided by r factorial over times n minus r factorial. And we recognize that as the binomial coefficient n choose r, which you may recognize from like Pascal's triangle or the binomial expansion theorem. So we can summarize these last 3 examples by saying that, first of all, the number of subsets of size r in a set of size n is n choose r. And we have that formula that expresses it in terms of factorials there. While the number of arrangements or permutations of r distinct elements from a set of size n is npr. And that, again, can be expressed in terms of factorials in the way you see there. So we'll be using a lot of these, we'll be using pretty much all these techniques as we continue our exploration of probability. And we will do that in the next set of slides. So we'll see you back there pretty soon. Take care.